You know, if I asked you to picture matrix multiplication, your brain probably jumps straight to this really complicated image, right? Rows slamming into columns.
Oh, absolutely. All those strict rules about dimensions and
Okay.
that classic gotcha that A times B isn't the same as B times A.
Exactly. It feels like this heavy, deliberate math. But here's the crazy part. The operation that actually powers everything from your phone's photo filters to advanced AI is, well, fundamentally simpler.
And that's our mission for today. We're going to unpack this thing called the Hadamard product.
Also known as the Schur product, right?
Yep, same thing. And we're going to see why this simple element-wise operation is just so essential to modern computing.
Okay, let's do it. So for anyone listening who only knows that standard complex matrix multiplication, how would you define the Hadamard product?
The definition is beautifully simple. The only rule is the two matrices have to be the exact same size, same number of rows, same number of columns.
Okay, so no weird dimension matching rules.
None at all. Then you just
Okay.
multiply the corresponding parts. The top left element in the first matrix gets multiplied by the top left in the second, the next one by the next one, and so on.
So if you have two, say, 2 by 3 matrices, you just multiply them piece by piece, and you get another 2 by 3 matrix back.
That's it exactly, which leads to its most important feature.
It's commutative. A times B is actually the same as B times A.
Right.
But if it's so simple, why does it get this really important sounding name, the Schur product theorem? What's the big mathematical deal?
That's where the real magic comes in. It's all about one word: stability.
Stability.
Yeah, a guarantee of stability. The theorem basically proves that if you take two matrices that have this desirable property, they're called positive semi-definite, their Hadamard product is also guaranteed to be positive semi-definite.
Okay, you got to pause there. What does positive semi-definite mean in simple terms? For me, for the listener.
Think of it like structural integrity. If a system is represented by a positive semi-definite matrix, it means the system is stable. It won't suddenly collapse or, spit out nonsensical results.
I see. So the theorem is like an insurance policy for model builders. It says, use this simple operation and your stable system will stay stable.
Precisely. And that guarantee is just incredibly valuable in these huge, complex systems.
And you can tell it's important just by how programmers talk about it, right? You don't get special symbols for things you barely use.
Exactly. I mean, look at MATLAB. It's a B. That little dot, the dot multiply, is just for this. Or in Python's NumPy library, the standard ab for arrays is the Hadamard product.
The fact that it needs its own special streamline symbol tells you just how foundational it is for high-speed computing.
And that focus on high-speed computation and efficiency is actually a perfect moment to mention our sponsor.
It really is.
This deep dive is sponsored by Silk. That kind of efficiency in handling massive matrices is what they do. So if you need help with AI training, automation, or even just figuring out where AI agents could make the most impact for your business, check out embersilk.com for all your AI needs.
All right, so we know what it is. We know it's stable. Where do we actually see this thing in our daily lives? I'm thinking image processing, for one.
That's probably the most intuitive one, yeah. Imagine an image is just a giant matrix of pixel values.
Okay.
And then you create a second matrix, a mask, with the same dimensions. Multiplying them together, element-wise, lets you instantly brighten, darken, or even completely remove parts of the image. It's also hiding in plain sight in JPEGs as part of the compression process.
But the really mind-blowing application, I think, is in AI, specifically in recurrent neural networks like LSTMs or GRUs. How can simple multiplication act as a gate for an AI's memory?
It's like a dimmer switch. These networks need to remember important things from the past and forget what's irrelevant.
Right, to understand context in a sentence, for example.
Exactly. So inside the network, you have a matrix representing the current memory. The gate is another matrix of weights between 0 and 1. You multiply them with the Hadamard product.
So if a weight is 0, the corresponding memory gets wiped out. It's forgotten.
And if it's 1, it passes through perfectly. It's remembered. It gives the AI this fine-grained dynamic control over its own memory. It's how they learn.
That is incredible. Such a massive technological leap built on such simple math. And I hear this even scales up into more complex things. Something about a penetrating face product.
That's getting into some pretty advanced stuff, but yes. What's so cool is that the Hadamard product becomes a building block. The penetrating face product uses it to do complex operations needed for, say, digital antenna arrays and in the deep layers of modern neural networks.
Wow. So we started with this really simple element-wise multiplication. the total opposite of what we think of as complex matrix math.
And it turns out to be the bedrock of stability, efficient code, and even the memory of advanced AI.
It's a true mathematical powerhouse hiding in plain sight.
It really is, and it leaves you with this kind of optimistic question, doesn't it? If a basic commutative operation unlocked so much of today's technology,
What simple mathematical tool that we have right now is just waiting to unlock the next generation of solutions?
exactly. The future is often built by understanding the deep beauty in the basics.
If you enjoyed this deep dive, please subscribe to the show. Hey, leave us a 5-star review if you can. It really does help get the word out. Thanks for tuning in.